Hello, Chem 111. This video is about the basics of how to construct a molecular orbital, or MO, correlation diagram, and how to fill that diagram with electrons in a molecule. So I'm going to go through two examples to do this, and the first example I'm going to do is the molecule N2. So to draw an MO correlation diagram, you have three regions of your diagram. So on the left and on the right, you will have the two atoms that make up your diatomic molecule. And I'll just remind you that this is an energy level diagram, so there's an energy axis going up. So what we'll do is we'll draw the valence orbitals for the two atoms. So there's a 2s orbital for each one, and then there are three 2p orbitals. Okay, and you should be able to know the electron configuration of nitrogen, which, as you'll remember, has 5 valence electrons. So it's a different color for my electrons. So each nitrogen atom would have two 2s electrons and then three 2p electrons. And it doesn't really matter what spin you draw on the electrons. I'm going to go ahead, just it sort of makes me happier to draw these in opposing spins just because they're going to have those spins when they make a molecule, but it doesn't really matter. If you drew all the spins on the right up, that's fine. You just have to accept that in the molecule, they might take on a different spin. Okay, so in the middle, it's a correlation diagram that correlates the atoms on the outside with the molecule in the middle. So the orbitals in the middle are the molecular orbitals that come from these atomic orbitals. And so you will have talked about this in class, but from the 2s orbitals, you get a sigma 2s bonding and a sigma star, or antibonding 2s. And sometimes in correlation diagrams, you'll see little dashed lines that go like this to show you which atomic orbitals they came from. You don't have to have those, it's fine. I'll draw them in this one and then not in the next one. All right, so now the 2p orbitals come together. So you'll notice we had two 2s orbitals, one from each atom. We end up with two sigma orbitals in that part of the diagram. We now are going to bring together 6 orbitals and make 6 molecular orbitals. And the pi orbitals that form from the 2p's are actually, for this molecule, N2, are lower in energy than the sigma 2p. And you'll probably talk about this a little bit in class. There's not really that much to say about it. There's just some mixing that goes on that makes this true. And then, the pi star orbitals are here, the antibonding orbitals, and the antibonding sigma orbital is the highest in energy. And again, we might show these lines. This just shows you that the bonding orbitals are in fact lower in energy and the antibonding orbitals go up in energy. Okay. And I'm not claiming that this is drawn to scale, so probably in fact it's not, but this shows you the order of the orbitals. All right, so that's what a correlation diagram looks like. And I just want to reassure you that we don't expect you to produce these energy levels in the middle on your own. They'll be given to you, so you just, but you'll get used to seeing them. Okay, so now to figure out what goes on in N2, we have to take all the atoms on the sides in the atoms and put them into the molecule, or all the atoms, the electrons on the sides, and put them into the molecule. So I'll start at the bottom. I have 4 electrons in the 2s part of this diagram, 2 from each nitrogen, so I have to put them in, and I go in order of 1, 2, 3, 4. Okay, so I just want to clarify that on the sides are my atoms, in the middle is the molecule. So these things exist in 2 different times, you can think of it. If you had the atoms on the side, they combine to form a molecule. Okay, so now I go up to the 2p part of the diagram, and I take those 6 electrons and I put them in. And the order you put them in follows the rules that you used in atomic orbitals, which is we go into the lowest energy first, And we first put one electron in each of those equal energy orbitals with their spins pointed the same direction. So that's 2, and then we do 3 and 4, and then finally we do 5 and 6. So we have filled the MO correlation diagram for N2. You can write an electron configuration for N2, and I'll just say that we don't really do this very often, but you might see it. So just so you know, you would say, it's sigma 2s2. I think we put parentheses around them. Sigma star 2s2. Pi 2p 2 pi, that we sort of identify these separately. Sometimes you'll see them called like, x and z, and then sigma 2p2, and then I'll just write not that useful. So really what we want you to be able to do is to draw the diagram like this, and there's a follow-up video that talks about some of the things we can do with the MO configuration. Okay, so that's N2. These only work, these particular types of correlation diagrams, we do them for diatomic molecules. You can absolutely make correlation diagrams for larger molecules. That's beyond the scope of Chem 111. If you take Chem 363, I think you might do a little bit of that. All right, so I'll do one more example, which is when the atoms aren't the same. So example 2, let's do carbon monoxide, CO. All right, so one of the things that happens when you have a heteronuclear diatomic is that the atomic orbitals are at different energies. And in fact, because oxygen's more electronegative than carbon, we would line its orbitals up at lower energies. So again, this is not going to be drawn to scale, but I'll approximate it. So we would have our carbon 2s here and our oxygen 2s, say, down here. They would combine to form, again, oops, that wasn't very dashed, sorry, a sigma 2s orbital down here and a sigma star here. The fact that I have oxygen lower than carbon is correct. It also isn't really going to influence your answer. So, and again, we don't expect you to draw these diagrams, these empty diagrams. We expect you to be able to use an empty diagram provided to you and fill it with orbitals. Okay, so again, in this part of the periodic table where carbon is, we have the pi orbitals are lower than the sigma 2p. I'll show those dashed lines there. I'm really not good at drawing dashed lines, is what we've learned here. And we have the pi star and sigma star up here. Okay, okay. So again, we want to start with our valence electrons in the atom. Carbon, as you know, has 4 valence electrons like this. Oxygen has 6 valence electrons, so it looks like this. And I went ahead and didn't worry about the spins this time. Okay, so now we put them into our MO diagram. Again, we have 4 valence electrons total in the 2s part. And now in this part, we have a total of 6. We have 2 from the carbon, 4 from the oxygen. Again, making the molecule. It doesn't matter where they come from. We just look at this and say, I have 6 electrons, and we put them in. 1, 2, 3, 4, 5, 6. So that's how you fill up molecular orbital correlation diagrams.